One other thing just to warn you guys before we get started is that the way that, so I have taught this in many different ways over the years. The way that I was planning to teach this class this time is mostly conceptual. So how to think about fMRI data and how to think about the steps of analysis that we do rather than how to do them. So some years we've taught this in terms of how to type the commands, like which variables to input into the MATLAB command. That tends to be more specific to whichever software package your lab happens to use. And so this time I was going to teach it just thinking about what the manipulations are and how to think about what the forms of the data are as we transform them through the different steps. So that meant this is going to be basically taught in pictures and words with no code or math is the plan. Having said that, the previous rule applies, which is any question you want to ask is fair game. And if this feels like it's too conceptual today, we can make it more concrete tomorrow if that's the direction you guys want to go. Also, the survey, thank you guys all for responding to my questions about what you were interested in. There were very clear winners, so we will definitely cover the topics everybody wanted to hear about, which included whole brain analysis and correction for multiple comparisons, and basic MVPA and classification analysis. That was everybody's top choice, so we will definitely do that, and we'll see how many of the other things we can also. Great. Okay, I'm going to have this as a safety net. Okay, so basic fMRI analysis. The first thing that I'm going to do is introduce you guys to how I draw and talk about brains so that you know what you're looking at when I make pictures. Oh, I didn't introduce myself. I'm Rebecca, and I have been doing fMRI research for 17 years. The very first time I got a scan of my own brain, I was a participant in an experiment in 1999 in England when MRI machines were incredibly rare and getting access to one for an undergrad was impossible except for as a participant. So I went as a participant to have my brain scanned by my mentors, and I fell asleep during their experiment, and I didn't tell them I did. I felt guilty for that for 18 years. And I've scanned a lot of people's brains, but probably the most important brain scanning experience I had is scanning my own babies, which I did over the last few years until they got too big to be scanned. Okay, so that's me and MRI. Okay, basics of MRI research. So the first thing I'm going to do is show you what a brain looks like when I draw it so that you recognize it. Okay, so that's a human brain for future reference. This is the lateral sagittal view. And what that means is that that's what you would see if you took the skull off my head right now. It would look just like that. So this is the frontal lobe. This is an eyeball, just so that we're all pointing in the same direction. Frontal lobe, temporal lobe, parietal lobe, occipital lobe. So that's my brain looking that way, the view you would see from the outside. So if all you did was take the skull off. This is also a lateral view of the brain, but now the medial view. Sorry, also a sagittal view, but the medial view. So what would happen if you cut my head straight down the middle and took a whole half of my head off, right? So this is also sagittal, just to say it's a view from the side. There's the eyeball pointing forward, but now it's medial, right down the middle of my head. Okay, this is coronal. Coronal view is what would happen if you cut my head this way and took my whole face off. That's the coronal view. And then this is axial. Take the top off and look down from above. Eyeballs this way. Good. I typically don't draw or frankly talk about subcortical structures or the cerebellum for the most part. I tend to pretend that they don't exist, which is obviously ridiculous. Okay, So that's the brain. Another bit of anatomy worth knowing. So this is cortex, gray matter, this is white matter. So this is axons. Axons, this is cell bodies mostly. Okay, and right, so inside these pictures, right, are lots, and this is the sulca, the gyrus. Okay, so your brain, right, extremely folded up. And so what we're going to think about mostly is we're trying to study the cortex, the function of the cell bodies and the cortical surface, which are all folded up inside your head, so that the tops of the folds are called the gyrus, and the inside the bottom of the fold are called the sulcus. Just getting basic vocabulary on the table so that we make sure if I use those words later on, we all know what they mean. Okay, that's the brain. Next, brain imaging. So the brain is a three-dimensional object. MRI data, as we collect them, are either 3 or 4 dimensions. And what we're going to talk about for much of this first session is how to think about those 4-dimensional data in different ways. So we're going to draw different pictures of the data as we transform them, getting rid of some of the dimensions at a time. So first we're going to build up the 4-dimensional data set, and then we're going to take different views of those data at different times. Okay, so starting with how do we get to 3 dimensions? So the way that you take an image of the brain, the first thing you do is take a slice through the brain. Slice or an image, and it's 2-dimensional. Somebody tell me which view that is? Axial. Okay, excellent. You're paying attention. Okay, so that's one axial slice through the brain, and that's a 2-dimensional picture. And this is the basic unit of almost all fMRI data that you will collect is the slice. So you have one slice through the brain. If you want a 3-dimensional image, then you take multiple slices. And so if you stack a whole pile of slices on top of each other, then that stack is now a volume. This is 2 dimensions. This is. Yes? So far we're clear? So you start with a 2-dimensional slice through the brain. You want a volume, a whole brain, a 3-dimensional surface, you take multiple of them. And that gives you one volume, a 3-dimensional picture of the brain. Okay. This is what you do for any anatomical imaging. So if you are interested in brain anatomy for some reason, then you will take a 3-dimensional volume usually. Very rarely just a 2-dimensional slice. Almost always, if you're studying a human brain and you're interested in its anatomy, you will make a 3-dimensional volume of that brain. And often, you will do that looking for the details of the structure, right? You're trying to see where the different folds are, how big the different parts are, sometimes how they're connected to one another. And if what you're doing is an anatomical, then what you're interested in maximizing is spatial resolution and signal to noise, right? So what you want is the most detailed picture you can possibly get of the anatomy of the brain. And the assumption is that the things that you're trying to study, like the shape of the brain, the size of the parts, where the blood vessels are, where the axons are, that those things change very slowly. They certainly change over years, right? For sure, you grow a brain and then it degenerates. But not in the time scale of a single MRI scan, right? You're neither growing your brain nor degenerating it over the course of an hour or two. And so the goal of an anatomical image is to spend as much time as you need to get the most precise image of the anatomy of the brain as you possibly can. Right? So that means increasing your signal to noise, increasing your spatial resolution, right? Making your I should say, by the way, one other term. So in a slice, you can think of the spatial resolution of the slice in terms of the smallest resolved element, right? Smallest point that you can tell the difference between it and its neighbors. And in an image, that's called a pixel. Cameras and stuff. Okay, and then when you stack that in a three-dimensional stack so that it has also, so it's a cube rather than just a square, that's called a voxel. So for anatomical imaging, you're trying to get your voxels as small as possible usually. And sometimes you're trying, if it's connectivity, we can talk about DTI if we get there. If you're trying to do connectivity images, then you're trying to measure that voxel as many times as possible so that you're measuring. Basically, when you're doing anatomical imaging, what you should think of is you're trying to get the most highly detailed picture that you can, and you're not worrying about how long it takes, right? So here what you're maximizing is spatial resolution. Which is made up of two things. It's made up of the in-plane resolution, how big your pixels are, and the interslice distance. Have how small your pixels are and how far it is from one slice to the next, and that gives you your spatial resolution. Does anybody know what the standard spatial resolution is for a standard anatomical scan at our scanner downstairs? Pardon? Yeah, so Day guessed 1 millimeter, AJ guessed 0.5 millimeter. I think it's actually 0.5 millimeter these days. Pardon? Oh, good. Well, so it depends on time. So some people might be using 0.5 millimeter and some people might be using 1 millimeter. Are you guys using something different?
1.
1? Great. Okay, so 1 millimeter isotropic, what that means, the word isotropic just means the same in every direction. So that means the in-plane resolution is 1 millimeter by 1 millimeter, and the depth is 1 millimeter. A voxel is 1 millimeter in every direction. That means you can distinguish whether it's gray matter or white matter in a given place from 1 millimeter away in any direction, for example. So the cortex is about 1 millimeter thick, right? Is that right? Yeah, approximately. Okay, so an anatomical voxel you can think of as more or less being able to plop down on a bit of cortex and separate it from the nearby white matter, or the other side of the sulcus, for example. Okay, so that is anatomical resolution, and the standard time it takes to take one for this image downstairs, how long does it take you to take one anatomical volume of the brain? 5 minutes, yeah. Okay, so you spend 5 minutes, because each slice takes a while at high resolution, and then you have a lot of slices. Is it 100 slices, the current one? 150? MP range that we're using now? 150? 176? Okay, so, right, 1 by 1 by 1 millimeters, 176 slices. Okay, so this takes a while because it's very high resolution, and then you take a lot of slices, and that combines to mean you take one volume of the brain in 5 minutes, right? With a DTI image, it might take 20 minutes to get one picture of the brain. Okay, these parameters change fast, so I don't know what right now. Yeah, I will get more into DTI later if you like, but in a DTI image, you're taking a picture of each voxel at each direction, each diffusion direction, and so you have to take many pictures of every slice. So you're asking, what are the limits on this resolution?
Well, that is.
Yeah, so Veronica's asking, is this as good as you can get, or there are things you can do to make an anatomical image better? And the answer is there's definitely things you can do to make an anatomical image better if you want. Some people, for example, would take 2, but you could also just increase your resolution here. So it is certainly possible to do a 0.5 millimeter resolution. It might be possible to do like 0.2 millimeters resolution. It would just take a long time. Once the in-plane resolution gets very, very small, you're fighting against poor signal to noise in each voxel. And that's especially a problem because at that size, pumping of the blood through blood vessels is important motion distorting the image that you're trying to collect. And so actually there are much higher resolution anatomical MRI images of dead brains because they don't move. And so you can put them in an MRI scanner for literally 8 hours and just take very, very, very high resolution images, being sure that that slice is exactly where it was 3 hours ago, right? Which you can't do with a living human. But so Bruce Fischel, for example, this is a thing that he does with fixed dead hemispheres, is you put it in an MRI machine all night, and you can get an incredibly high-res MRI image. So this is not limited by the machine. It's limited by what you're trying to achieve and the intrinsic motion of the brain and the tolerance of the person, if they're alive. Their tolerance goes up when they die. Okay, so that's anatomical imaging. And Veronica's question is exactly on point, which is to say these parameters are set for convenience, right? So if we take a 1 by 1 by 1 isotropic MP-RAGE anatomical image, if that's what we're doing, we decided that image is good enough and quick enough. It's a trade-off. It used to take us more like 12 minutes to get one anatomical image, and it is possible to get an anatomical image in 30 seconds. And so basically you're making a trade-off. The longer you take, the higher the spatial resolution you can get. How long do you want to spend? And the current trade-off that most fMRI researchers are using is something like this that says around 5 minutes, that's a good enough image for the things that we want to do with it. And we don't want to spend all of our scan time getting a better one because these data are often not the data we're most interested in. We're using these for basic reference, and so we want a pretty good image, but we're not using them as the core of our analysis. Labs whose interest is in brain anatomy will do a lot more anatomical imaging. Sometimes that means different kinds of anatomical images. Sometimes it means more of the same kind so that you can average them together and so forth. Okay, more questions on anatomical imaging? We've done this, I know, extremely briefly. It's mostly for contrast. You can also come back to it. Okay, the main reason we're talking about anatomical imaging is think of it as a reference for comparison to functional imaging. So this is one volume, right? All the stacks that make up one brain. And functional imaging sequence of those three-dimensional images. Time. It's 4-dimensional data. Right? 2 dimensions of a slice, 3 dimensions when you stack them. Do that again and again and again. Time is the 4th dimension. Yeah? Okay. So that gives us another parameter of resolution, which is temporal resolution. How fast can we get back to the same point again? Right? So now we want to know how close can we discriminate in space, but we also want to know how close can we discriminate in time. Right? We've measured a brain region's amount of activity at one moment in time. How long will it be till we can measure it again and again? Right? That's temporal resolution. And the unit is this amount of time, right? The time from when you take one image to when you take that image again. So you can think of that as the time from taking one voxel to getting back to that same voxel, right? You're in one voxel, then the whole rest of the brain, when do you get back to that same voxel? Technically, it's actually a slice that you come back to, not a voxel. One slice, you go through the whole rest of the brain, when do you get back to that slice? Okay, so that unit, the temporal resolution, but also the repetition time, what is a typical value for that at our scanner? Okay, so you can compare 2 seconds to 5 minutes. That's how long it takes to take one whole picture of the brain in these two different modalities. Okay? Now, in order to be taking a whole volume in 2 seconds instead of in 5 minutes, then we have to sacrifice spatial resolution. Okay? So the temporal resolution, to get that to be seconds, then spatial resolution is typically downstairs. Typically, this isn't always true, but standardly about 3 by 3 by 3 millimeters and something like 30 slices. And that gives you 2 seconds. Awesome. That's a great question. So let's think about the costs and the benefits of having our voxels be. So first of all, how much bigger is a voxel in this scan than in this scan? 27 times, right? One voxel here is 27 times bigger than one voxel here, right? Because it's 3 voxels in every direction. So 27 anatomical voxels make up one functional voxel, right? And the anatomical voxels were already pretty big relative to cortex. Anatomical voxels have tens to hundreds of thousands of neurons in them, times then 27 to a functional voxel, right? So a single functional voxel has hundreds of thousands of neurons in them for sure. It also almost always isn't not just inside the cortical sheet, but often extends out beyond it. Sometimes bleeding across the walls of sulci, sometimes going into the white matter, right? These voxels are big compared to the structures that we're trying to study. I think I drew the anatomical voxel. I think the cortical sheet is more than 1 millimeter. I've set this factor wrong by something. Okay, but in any case, this is still definitely a problem that the voxels are so big. Okay, so Samuel's question is, well, so why did you do that, right? Why did you sacrifice all this spatial resolution in order to get your temporal resolution close to 2 seconds? So we'll come up with a partial answer, and then we'll think more about it as we go along. But first, let's think, so 2 seconds is the temporal resolution we have. Let's think about the temporal resolution we want. Principle, we're interested in studying neural activity, right? Neuron in the brain. Do you guys know approximately what's the temporal resolution of neural activity? How long between spikes in a neuron? Around 3 milliseconds? Yeah. So the resolution we want is half the resolution of the thing we're trying to measure. So if the neural firing is every 3 milliseconds, we want to be measuring it about every millisecond, right? So we want to be measuring this about once a millisecond. Okay, we're definitely not doing that, right? So this number is both small enough that we're sacrificing spatial resolution and big enough that we don't have a hope in hell of seeing neural activity, right? Okay, and so obviously it's a trade-off of some kind. And so what we're going to come back to is, what is this a trade-off about, right? Why was 2 seconds something worth achieving? You can also, Veronica's question, can you go faster, right? And you certainly can go faster. So we'll talk about both. Is this fast enough for anything, considering what we're trying to measure happens every 3 milliseconds? And should it be faster? And what would happen if it was faster? So we'll think about that as we go on to what's the signal that we're measuring. But it's definitely worth thinking about. You certainly could go faster. You certainly could go slower. If you went slower, you could have higher spatial resolution or more slices. If you went faster, you'd have to have lower spatial resolution or less slices. Sometimes slices is called coverage, right? Because you can imagine with fewer slices, you cover less of the brain. More slices, you can cover the whole brain. Coverage used to be a big thing in MRI. In the late 90s, early 2000s, the way that people got even remotely acceptable in-plane resolution was by not covering the whole brain. So back in the very early day, if you look at like Nancy's first papers, she covers half the brain. And that was the sacrifice to make the TR fast enough and the in-plane resolution fast enough, was that you couldn't get all the way through the whole brain and get back in time to get a deep image again. And so her early papers cover half the brain. Then the scanners and the computers got faster, and so whole brain imaging got standard, although in my lab it is still standard not to cover the cerebellum, whereas other labs think that's crazy. It's a whole enormous brain structure we routinely sacrifice. Okay, so coverage, resolution, and temporal. So basically, the first thing to think about is that four-dimensional fMRI data, when you collect it, is always a trade-off in terms of the different kinds of resolution you were trying to achieve. You had to decide how much spatial resolution did you want, how much temporal resolution did you want, and how much coverage did you want. And those parameters set the four-dimensional resolution of your data. Clear? Okay.